Hello everyone. Before I go on to the math, I want to show you a more interesting example of variational autoencoders for generative purposes. So in particular, we're going to start doing this cat doesn't exist. So from tons of examples of cat faces, I'm going to try to create a model that can generate from random samples in the latent space some random cat that wasn't actually in the original set of images. So it's going to learn to generalize from a distribution of a bunch of examples we have to new things, new unseen examples. So what I did was I jumped on to Kaggle and I grabbed a data set of 64 by 64 cat images. And here are the cats here. So there's 64 by 64 color images. And here's a bunch of examples. So you can see they've all been cropped to the cat face to make it easier, and the eyes are pretty much centered. But there's still a lot of variance there. So, all right, what I did then is, actually there are about almost 16,000 of these cats. And so what I did was I created a custom data set here where I just made sure the images were actually 64 by 64, converted them to torch tensors. And when I pull out the first image and look at it, what I'll see is that it is indeed, it has 3 channels, and it's 64 by 64. So that's cool. If I want to actually look at that image using NumPy and Matplotlib, what I'll do is I actually have to switch this color dimension to be the third dimension. So the channels dimension actually needs to be the last dimension for NumPy. So I'll say x is equal to np.move axis x02. And let's take a look at that. And so there's our little cat friend. That is the first cat in this data set. All right, but I'm going to use pretty much the same model that I had. I'm just going to tweak some of the parameters here. So now these are color images, so I'm going to take 3 channels in. I also have to think carefully about the latent space here, because 2 dimensions is probably not going to cut it. Even though these cats have been cropped to the same region, there are probably more semantic dimensions to describe them. So what I mean by a semantic dimension is something a little bit higher level that describes the degrees of freedom that we have in the image. You know, in the original image we had 64 by 64 by 3 numbers, and that's probably a little bit over complete to describe the full cat image. But still, we're going to need to know things like the color of the cat, which perhaps is 3 dimensions. We might need to know something about the breed. I have no idea how many dimensions that is, but let's just say 4. Maybe the eye color. Maybe that's something that's independent of the breed, so that would be another 3. So we're already up to 10 dimensions there. Maybe something about the lighting in the surrounding environment. And if it's just ambient light, that would already be 3 dimensions. But it could be directional light, in which case you would also need the position of the light in the direction. That would be an additional 6 degrees of freedom, or 5 at least. So anyway, the point is there are many semantic dimensions that are independent. And somehow this is like a lower bound. I mean, unless these actually are correlated. But assuming these are independent, you know, all the dimensions here that I can come up with are sort of a lower bound on the number of dimensions that I should expect to have in the latent space. So I don't know, I just thought of another one, whisker length. So maybe that's an additional 1 dimension there. So I don't even know if I've gotten them all here. Just to be safe, let me create a latent dimension of 64. So a lot bigger than we've been dealing with so far. But yeah, and then also I realized that these are now 64 by 64 images as well. So I'll use 64 dimensions in the latent space, but actually the input is 64 by 64 by 3 channels. Okay, another thing I'm going to change, well, actually I'll keep this, I'll show you what the result is like with this first, but I'm going to want to increase the number of channels that are involved too. I want this model to be a little bit more powerful, to have some more parameters. So I'll have more kernels involved eventually. Okay, but most of this I can keep the same. There's just one more little thing I want to do here. So I'd like to create a method that samples from the latent space. And I'll ask for some number of examples. And so the purpose of this method is to sample from the latent space and generate the images from the decoder. So if I go back to my picture, what I'm saying is, okay, so I had, you know, this latent space that I've learned, and I want to just randomly pick something. You know, if I'm using this prior of each dimensional latent space has mean 0 for the Gaussian, standard deviation 1, that means I'm going to generate a number with rand_n for each dimension, and that's going to be my latent vector. And then I'll just send that through the decoder and get an image out. So going back here, what I'm saying is, oh, and actually let me also pass along the device that this is on. But yeah, so I'll say here, I want to create a Z which is sampled for each dimension from the, oh, I forgot, in Torch, it's actually just rand_n directly. It's not within a module there. So I'm going to generate samples from Gaussian with mean 0, standard deviation 1. And so I'll say, okay, I'm going to generate a sample for each dimension. So that's going to be self. So I have, okay, first of all, number of examples. That's going to be along the batch dimension here. And then for each example, I want to generate as many dimensions. I want to sample as many dimensions as there are dimensions in the latent space. So I'll say dim latent. And then I'll say .to device. It may be that I'm using the GPU here, so I want to make sure I put that on the GPU. And so then all I have to do is say return self.decoder Z. Okay, so let's see about this. If I were to create the model with these default parameters here, if I were to say model equals convolutional autoencoder, what's it? Yeah, or conv autoencoder, and then I'll sample from it. So now if I say x est equals, or x gen equals model.sample, let's say maybe 16 examples. Yeah, I have to say the device too. I'll just start with CPU here. Dim latent, I should have said, this is an instance variable of the class. I should have said self.dim latent. Okay, there we go, finally. If I look at the shape of this, what I have are 16 examples of my color images, 3 by 64 by 64. So what I'll do, I'll make a little method to plot these 16 examples on a 4x4 grid. And then I'll train this, and we'll have a look and see. At the end of each epoch, I'll randomly sample 16 examples, and we'll have a look and see how they're looking as the epochs go along. So let me pause, and I'll do that training. Okay, so here are the results. Here's the first epoch, which they look pretty darn blurry. You can't really see a whole lot. But as the training progresses, and I keep sampling from my latent space with a Gaussian, because that's what the prior was, right? I just sample each dimension with a 0 mean, standard deviation 1 Gaussian. And these are cats that I've not necessarily seen before. This is just coming from the overall distribution. So you see, as I go through and I keep training, they become a little bit clearer. Now they're still blurry, and this is a known issue with variational autoencoders, because if you look at the way that I'm assessing fit to the data, I'm just summing the squared differences there. Actually, that would be the fit for a log probability of a Gaussian prior, by the way. Because you notice in the Gaussian, if I go back to the equation, actually it's negative square root of x minus mean quantity squared. So if the mean represents a correct pixel, x, and then x out is what I get, I take the log of that and I get the quantity squared, and up to a constant. The other things come out. So anyway, with the Gaussian prior, this is what you would have as the loss function. And you look at that, and it kind of puts all the pixels together into one big pot. And so what it means is maybe higher frequency details are not going to necessarily be promoted with this loss function. This cares more about sort of the mean and lower frequency components of the image. So yeah, it's kind of a known issue with that representation of the fit, that these are going to be blurry. Just for the heck of it though, let me see what happens. So yeah, I ended up with a loss there of a fit loss of about 182 after 30 epochs and a prior loss of 1.88. Let me just try this again one more time. I'll start out with 64 channels to begin with. So a lot more channels at the beginning. And I'll train this and see if those additional parameters help me to do a little bit better. Okay, so we look at the results and really they're not that different. Actually, one thing I had to do here was I had to decrease the learning rate a little bit. The learning rate before was actually 1e to the -3. I had to dial it down a little bit to the apparently magic number for Adam, which is 3e to the -4, because the model got more complicated. So I was, doing that whole thing where I jumped around too much. Okay, so I was looking back at this code and I noticed a couple bugs that I made. So one of them was, remember I said that having a nonlinear layer makes the network much more powerful? I completely forgot to put in the nonlinear layers in my decoder. And the other thing I had a bug on was this was I is less than depth minus 2. I was accidentally including too few channels in the second to last layer. Now that makes a huge difference on the final result. So I knew the cats were going to be blurry, but they weren't as blurry as I was showing a moment ago. This is more the result you would expect. So I've updated the code in the link, and anyway, I think these cats look much better. Although we'll see if we can improve them any more with other tools.